61B. Hope you had a good time. So midterm score, 2 scores are out. As I mentioned in the post, pretty hard exam. I mean, it's like moderately harder than we had been targeting. So if you're a little lower than you wanted, then don't feel so sad about that. Uh-oh, my screen went away. It's coming back, I bet, though. Anyway, yeah. So regrade requests will be opening April 4th, and then we'll go away on April 9th. If you're like having stress about course stuff and you want to meet with one of us one-on-one, there's a Piazza thread here where you can come ask us questions. Maybe I'll try and drop in on some of those so we can give you some advice. That's that, I think. So, all right. Moving on. So today we're going to be talking more about graphs. Hopefully you had a chance to check out previous lecture where we talked about depth first and breadth first traversals of graphs. And I'll do just a quick, very, very quick review, but I'm assuming you've already seen that last Friday's lecture. If not, you'll pick up some of the details, but definitely catch up as soon as you can. So suppose, for example, so graphs, right? We said that this useful data structure for tracking objects that are connected in space, for example. And suppose we want to collect a list of vertices that are reachable from some start, say 0. We've talked about 2 different approaches to do that. One is depth first search, and the other is breadth first search. So a question for you. And maybe this is a moment to have someone next to you tell you what these things are. Hopefully there's not many of you there in that bucket. But a question to consider is, do both of these work for all graphs if I just want to find what's reachable? So for example, 3 is reachable, 6 is reachable, 8 is not reachable from 0. So do both of those work for all graphs? That is depth first and breadth first search. And is one better than the other in some way? So think about that for maybe 40 seconds just to get warmed up for the day. Okay, what do you think? All right, some thoughts. Do you think they'll both work for all graphs for this reachability problem? Or maybe the other question might be a little easier to address. Can you imagine cases where one might be better than the other? Yeah, sure. Someone. I hear some muttering here. Well, let's say we're still only trying to do the problem of reachability. Yeah. So breadth first seems better because you see a wider range of nodes, so you feel like you're going to see what's reachable sooner, but they still have the same asymptotic runtime to complete. So it's not that it'll be faster. I mean, it feels more intuitive, but actually both of them will work on any graph. Can anybody think of any graph where one of them might be better than the other? Yeah. So breadth first gives you the shortest path. So if you care about the ordering, then that seems maybe better. But if we just care about is it reachable or not, it doesn't much matter. But you're right, breadth first search kind of gives you 2-for-1 deal, right? You don't get just what's reachable, but you also get the fastest way to get there. Hi.
It's not showing up on the graph because we're HDMI.
Oh, you want me to switch over?
Yeah.
Okay, switching. Thank you. Okay, no problem. Okay, anybody have any thoughts about a graph where one is actually somehow... So breadth first is better in the sense that you get the distance as well, the shortest path. Any other thoughts? Yeah. Yeah, so the memory usages could be different. Okay, so I had that on my slides. It'll pop up shortly once I push the magic button. So they both work for any graph if we're not going to run out of memory in some way. But the performance can depend on the situation. So if we have a graph that's very spindly, depth first search can be a little worse because it uses a ton of memory for that deep graph. And breadth first search can be bad for graphs that are really bushy. Like say you have 1 million vertices and they're all connected to your start vertex, then they might end up on the queue all at once, and that could be costly. I guess I should also say, I hadn't thought about that before your point, which is breadth first search gives you a 2-for-1 deal. Also get shortest paths as a bonus. So maybe you decide you want that as well. Okay, so the point here we have two hammers. We have depth first search the hammer and breadth first search the hammer. And for the purposes of finding what's reachable, Okay, well, both are about equally good. In these sort of corner cases, one could be a little better than the other, but they're basically both pretty good. Now, there are some circumstances where the difference between depth first search and breadth first search really counts. For example, if we care about shortest paths, then BFS is definitely the choice. But we're just talking about reachability. They're both pretty good. Okay? Those are the kind of questions, by the way, that I encourage you to be asking yourself, the weird questions that I think prepare you for hard midterm problems. So we had some other graph problems. We had, for example, this idea of a topological sort. I'm not going to say what that is at all. But in that case, we really needed to use depth first search. When it came to the question of shortest paths, we wanted breadth first search. Okay? So the point here is just to say there's multiple tools. Sometimes they're both good. Sometimes one's better than the other. And we're going to now go even further than just old DFS and BFS. So any questions about this before we continue onwards? All right, cool. Okay, this was before lecture. Actually, this is actually from Friday, so it's one lecture ago. We discussed, well, let's say we're trying to solve a real-world problem. We want to do driving directions from here to Davis or whatever. Would breadth first search be a good algorithm if our graph consists of vertices, which are intersections, so the intersection of Shattuck and University, and edges are roads, so the road between Shattuck and University over to Shattuck and, I don't know, whatever was the next one over. So in that case, is the breadth first search that we've discussed in class, would that be a good way to do this? And we actually gave the answer last time, which was no. Why? Because number of intersections isn't the right metric. Maybe taking a 2,000-mile detour on the freeway to save an intersection is not a good idea. So minimizing intersections does not minimize driving time. Okay? So what we're going to talk about now in this lecture is how do we actually address this problem? How do we augment our graph model to include, for example, the length of roads, which really matters. If you want to know whether or not to drive that way or that way to get somewhere, you care about the length of the roads to the next intersection. Okay? So we're going to introduce an old algorithm known as Dijkstra's algorithm, and then we're going to talk about an improvement on that. And the basic picture here is that we're going to now augment our graphs where every edge is going to have a weight. And that weight in the context of driving directions, that's going to say the time it takes to get from this intersection to this one on average is 2. So maybe it's a relatively short road or it's a long road with a fast speed limit, whatever. But this number just is supposed to represent the time in the case of driving directions. But for the moment, we're going to think of it more of just a math problem. Okay? So the most obvious question you might ask yourself about a graph like this is, if I have some source and some target, right, Berkeley and, 5 is Davis, then if I want to find the shortest path from that source to target, how do I do that? And so the first thing I'm going to point out is that the solution to this problem is always going to be a path on this graph, and it's never going to have any cycles. So we're never going to have some kind of loop. Why won't we ever have a loop like this? So if we're trying to get, say, driving directions. Yeah, just don't do the loop. So if I give you driving directions that involves driving in a circle, just don't do that. And I promise you'll still get there, and you'll get there faster. Assuming there's not a wizard or something who will destroy you for disobeying the rules. Okay. So this problem always has a solution. It's a path with no cycles. And similar to what we saw in the previous lecture, the way we store our solution is we have a distance to array, which tells you the distance from our source to each of the things we see along the way, and an edge to array saying how you got there. And that's very similar to what you had on homework 4. Okay? Let's suppose you didn't want to just find the directions from the source to one particular target, but instead you wanted multiple targets. And the reason I'm going to do this is because you can get this seemingly much harder problem, the solution to it, almost for free. Okay? So let's suppose instead we have the shortest paths to every other vertex. In this case, it's kind of interesting to observe that the solution is always a tree. So whereas if we try to get from point A to point B, it's always some path without cycles. If you're trying to get from a source to literally everywhere, so I want driving directions from Berkeley to everywhere in the country, it turns out that solution is always a tree. Okay? That is, it is a subgraph with no cycles in it. And what's nice about this is it actually ends up being a pretty compact object. It seems like if I said, hey, Josh, give me driving directions to everywhere, you imagine that would be a pretty significant data structure just to hold all that. But it turns out it's not so big. How big is it going to be exactly? Well, that's a question for you to think about in a moment. Okay? But first, before I ask you about how many, I actually want to tell you why it's a tree, because that's not obvious, okay? So why is the solution to the driving directions to literally everywhere in the entire world that's reachable, why is that a tree? Well, one is, of course, it includes, we can't have cycles, so there's no reason to go in a loop. That would be crazy. And the other thing we need for it to be a tree is that every node has to have one parent, okay? So in other words, if we're looking at the driving directions to some place, there's never going to be the shortest path that involves both of these. The reason here is, well, how do we know that? I guess that's something I want you to think about for 20 seconds. So if I'm giving you driving directions, why are the directions to everywhere not going to involve two arrows that go to 5? It's a little subtle. So maybe spend 30 seconds figuring out what the question even is, and maybe come up with an answer as well. Okay, this one I'm just going to spoil. So in this case, let's say that one of these paths is longer than the other from the source, right? Like that the total weight to get down to 5 from this path versus this one, if one of them is longer than the other, it shouldn't be part of the solution. You should just have the other one, right? So suppose this one's actually shorter than this one, you should have gone this way. Now, if they're the same, right, you might say, oh, well, Josh, maybe the directions just happen to be that there's 2 ways to get to 5. What I would say is you should just pick one arbitrarily. You just don't include this one, this edge right here, this 4, for example. Okay? So the solution to the problem of finding the shortest path from a location, say Berkeley to everywhere else, the answer is a tree. Now, here's a question for you to make it a little more concrete, and then I'll take questions after you've had a chance to think about this. Okay? So this time, we have a yell key question, if you want to try and answer it online. So if G is a graph, which has V vertices and E edges, how many weights are going to be in the shortest paths tree of G for some specific starting vertex, say 0? So think about that question. Turns out to be a specific number. Just a couple more seconds. Just gonna wait for a few more responses. Okay. So before I answer this question, let me point out something important here about the shortest paths tree. What it tells you, as I said earlier, is how to get anywhere. So for example, what is the path to get to 6 from our source, looking at the shortest paths tree? How do you get there? 0, 1, 4, 6. Okay? So if we think about, and since there are no cycles in this thing, it's a tree. If we have a tree where every vertex has exactly one parent, and there are V vertices, or V nodes in the tree, how many will there be? So everybody has one parent, except the root. And there are V things. So how many lines will there be? V minus 1. So the answer then is just V minus 1. For every vertex, there's exactly one edge that points at you. Okay? And what's interesting here is this tells you how to get from 0 to 1, how to get from 0 to 2, 0 to 3, 0 to 4, 0 to 5, and 0 to 6. All compactly in just V minus 1 edges. So in other words, if you wanted to make directions that go from Berkeley to literally every place in the country, the total size of that object to capture that information about how to get everywhere would just be the number of places minus 1, which isn't so bad. Any questions about this? So again, at first glance, it seems like it should be a more complicated thing, right? Like, if you need directions to everywhere, it shouldn't just be the number of places minus 1, but it is. Okay. Yes. So is there a different shortest paths tree for each vertex? Yes, in fact. So for example, the shortest paths tree from, 3 would be some other different entity. And you'll note there's a little bit of a corner case here, which is some objects are inaccessible. So there was an assumption I was making that every vertex is reachable. So maybe some of you were like, well, what about 3? Then the shortest path tree will be smaller because you can't actually get to 0. Okay, point taken, but, I'm going to assume all places are reachable in general. Yeah. In this case, it is a coincidence that it's half the number of edges, yeah. You can end up with a much denser graph than this. All right. Great. Oh, yeah. V minus 1 is the number of edges in the shortest paths tree, so it's a number of black lines. V is the number of vertices in the entire graph. Yeah. Now, there is a little tiny thing. I'm going to note here. Assume every vertex is reachable. Okay, because if it's not reachable, then it's going to be the number of reachable vertices minus 1. Okay. All right. It's a minor point, but I think an important one. Yeah, one more. Why are some specific arrows bolded? These are the arrows that are part of the shortest paths tree. It'll become more clear, I think, once we do a problem. Okay. So here's a specific graph for you. I'd like you to try and find the shortest paths tree for the graph below. And actually, I need to tell you what the source here, it's very small. It says S is A, so source is A. Just to make that very clear, because I realized it was very small. Okay, so try and find the shortest paths tree. In this case, it's going to be a very simple object, but hey. So the object you give will give the shortest path to every other vertex from A. All right. Here's what I came up with. That is the shortest paths tree. This tree is very spindly, right? No branching at all, but still a tree. Just a trivial one. And what I'm going to do throughout the rest of the lecture is I'm always going to annotate in magenta the total distance from the source. So you'll notice that I put a 1 next to C, a 2 next to B, and a 4 next to D. Okay? So this is the shortest paths tree. Anybody disagree or have questions? Yeah. Anyway, we can decide. The question is, how do we decide to do this particular tree? Well, let's suppose we had included 5 as well. Like, if I add this as well, because this was just you guys using your intuition. I haven't given you an algorithm yet. But if I did that, what's wrong with that? Why is that not the shortest paths tree? Well, it's not a tree. Okay. Let's say I used 5 instead of 2. What's bad about that? That's not the shortest path to D. Yeah. Yeah, it would take 6 instead of 4. So I haven't given you an algorithm yet, but this is the shortest paths tree for this particular object, starting at A. All right. Happy? Okay, so let's start talking about algorithms to do this. You guys made up something, like you just used your intuition. So when we're trying to do problems on graphs, what are some of the ways we approach them? We have 2 types of things we've done so far, 2 hammers, so to speak. Breadth first and depth first search, right? So we could try and use one of those. I'm going to pick depth first search. You might already feel like that's a bad idea because it doesn't get you shortest paths, but I'm going to do it anyway. So how do we find a valid shortest paths tree? Well, one approach is, let's just traverse the graph depth first, And then we'll add an edge to the shortest paths tree. We'll make it dark black if the target vertex at the end of that edge is not in the shortest paths tree. So basically, we look at A first, and we say you got 2 vertices that you can see. So that's now the shortest path tree incorporates 5 and 1. This algorithm does not work, by the way. It's incorrect, but it's just a place to start. So I do depth first search, and I say 1 and 5, you are now part of the tree. Great. Okay, who do we go to next? Well, let's assume that we just go in order of the adjacency list of A, and let's say B's first. So we do B next. So B, we look at our neighbor, we see that this edge gets us to D, and at this point, we don't have anything else that we're going to do, because the next edge to be considered, if we're doing depth first search, we'd have D, and then, I meant to have both of these done. Sorry, I changed the color before lecture because I thought it would be more clear, but I just realized now doing it in front of you, that's confusing. Okay, so after this, depth first search will process D, then C, and then we're done. Okay? And now we end up with this wrong tree. So this algorithm doesn't work, but we can tweak it to make it a little better, right? So for example, okay, so actually, you guys, hopefully you all see that this is not the correct shortest paths tree. So I'm going to make a tweak to this to make it a little better, and I'm going to introduce a notion known as relaxation. Okay? So one of the problems we encountered is that, actually, let's look back here. Whenever we processed C, we didn't consider the fact that 5 made a better path than what we had before. So really, I mean, when you consider what happens when we process C, it was only because we'd already noted D as reachable that we didn't update this distance. Okay, this will make more sense once I do this. Sorry, I thought that would be helpful, but I think it was just confusing. So what we're going to do now is the exact same process. The only difference is that when we consider a particular edge, we're going to replace an old edge if it's better. Okay, so let me make sure that this will make it very clear once we just do it. All right, sorry. So same as before. We start our depth first reversal. This has a distance of 5. This has a distance of 1. Okay, we move on to B. Well, when we process B, the distance here is made 7. And then when we get around to C, when we're doing our depth first search, at that point, the difference between this algorithm and what we had before is that these outgoing edges, we actually have found a better path, right? I mean, if we look at what we had before, the distance here was 5, but when we process vertex C, we can see that the distance, if we go 1, 1, to this vertex, the total distance, if we use this new edge we've just discovered, would be better. And likewise over here. So in other words, we've replaced these 2 edges with these better edges. Okay? So this is a better algorithm, but is it correct? No, right? It's still wrong. But it's still, like, you get the sense that it should behave better. What's the issue here? Well, we switched away from 2 because 5 was better. Why'd we do that? Like, why didn't we just leave it as 2? Well, we did that because we were thinking locally. We weren't like considering the whole global situation. So one fix for this would be, we could then, okay, well, let's rerun the algorithm from B. We could do some kind of like rerunning over and over. But this algorithm is, one, hard to prove that it works if you try and revisit all of your neighbors. And the other is that the runtime would suffer. Okay? So this algorithm is also not great. But it's still a step in the right direction. Okay? So now I'm going to introduce a third approach, which is, rather than just using this one improvement relaxation, we're going to do something else known as best first search. Okay? So this is actually not depth first search. It is not breadth first search. It's now a totally different thing. And how it's going to work is we're going to consider our vertices in the order of their distance from the source. Okay? So what's the closest thing to the source? The source. Good. Okay, so we'll start with the source. We'll do the exact same thing we've been doing where we say, you guys are part of the shortest paths tree. But now, which vertex should we go to? C or B? C. C is better. It's closer. Okay, so we go to C. Once we consider C, we'll note that the new distance to B is better. So the total distance here is 1 plus 1 equals 2. And then 1 plus 5 equals 6. And then who's next? B or D? B. Good. So we do B, and we look at B's outgoing neighbor, and we see that it's going to be 1 plus 1 plus 2 is 4. Okay. Now, one way I can note here, the distance to B is 2, so I don't actually have to like rewalk the entire path. I know my own distance from the source, so I could just say 2 plus 2 is 4. Good. Okay. Which is something I assume you guys learned earlier. That 2 plus 2 is 4. All right. Bad joke. All right. So I know, who's here visiting for like, potential students? Okay, cool. You knew the 2 plus 2 is 4 thing, right? Good. Okay. All right. All right. Let's see a bigger example. Okay, because I think it's maybe not so clear on such a tiny example. Let's just use the full force of Google Slides and do a huge example here. Okay, maybe we would have that cool laser. So yeah, bam, yeah, it's there. Good. Okay. So the implementation of Dijkstra's that we're going to use is the same concept I was using before, but now I'm going to make it really concrete. We're going to, similar to before, we're going to have a fringe, the set of vertices we're considering maybe using, and we're going to start by inserting all the vertices in the fringe, and we're going to give them the distance we know so far, which for all of the vertices is going to be infinity, except the source itself, which will have a distance of 0. And then what we're going to do is repeatedly remove the closest vertex, take the best vertex, and then relax all of its edges. And relax, I said out loud just briefly, just means use the edge if it's better. So when I say relax, it means use if better. And it relates to this idea of like, if you have a rubber band and you let go of it, it like relaxes, right? It just goes to wherever it needs to go. So if the new configuration, when you let it go, is smaller, it'll shrink down. That's the physical analogy. All right. So the first thing to come out of the priority queue is 0. We put it in and we take it back out immediately. And now we have 2 edges to consider. So the distance to 1 from 0 now is going to be 0 plus 2. Is that better than infinity? New guy. It's better. Good. Wow, they're teaching you well. All right. And then 0 plus 1 is infinity, which is also better. So I'll say, okay, we're going to change these edges are now going to be incorporated into my shortest paths tree. Well, how do I record that information? I could just write it out as an edge to array. Okay? So right here, my shortest paths tree is captured so far just by these 2 numbers. It's a little tiny tree with 2 little branches. And it just basically says, to get to 1, take 0. To get to 2, take 0. And these are the best known distances. And then I also update the priorities in my priority queue. So my fringe now says vertex 2 is distance 1. My vertex 1 is distance 2. Okay? So who's going to come off this priority queue next? Who's closest? Correct. 2 is closer. Okay? 2 has only 1 outgoing edge. There it is. And so this new distance, what do you think it might be? See, 15, but that's not the total distance from the source. We also need to consider 2's distance. So that's going to become 16. Okay, so then what we'll do is update the priority of this vertex to say it's 16. That's its distance from the source. We'll update its distance value, and we update edge 2. So we're updating 3 total values, 16, 2, and this value here. Okay. All right, onwards. The next thing to come out of the priority queue is 1. So then we have these 3 edges to consider. Okay, well, I'll do a bunch of math for you automatically. So this distance is going to be 13, which is better. So 2 plus 11, 13. 2 plus 3 is 5, which is less than infinity. And then 5 plus 2 is 7. So what's going to happen here? Should we use this edge? No, not good. So these will get replaced. And so we're changing the edge 2 values for 3 and 4, but not for 2. The best way to get to 0 is still... the best way to get to 2 is still 0. Okay? And we update these 2 priorities. They're in the priority queue. Okay? Now what we'll notice is that the priority queue is only those vertices which have not been yet considered. They're still green. Okay? So the green is just basically a way of saying it's in the fringe or not. So which vertex is next? 4. That's the closest one. And so now the question then is, after I consider this, what I'd like you to do now, if you can do this, you understand Dijkstra's algorithm. Okay, so I'm going to give you guys 80 seconds to do this. So figure out what's going to change in this array, and in the fringe. Twenty more seconds. All right. So there's some values that are on the chopping block. Everything in this 2, 5, and 6 row, any of those could potentially change. And then same deal with the fringe. 5 and 6 could potentially change, but 2 is never going to get put back. Okay. So important point, the fringe never grows. It only ever changes values and shrinks. Okay. So we consider this one here. This is basically row 6. So what's the new distance 2 going to be here? 10, I hear. Because that's 5 plus 5 is 10. And the new edge 2 will be 4. Okay? How about this? Will this change? Yeah, 4 plus 5 is better. So that's going to become 9. And then will this change? No. Okay? So this is what you should have ended up with. The priorities for 5 and 6 are updated to be 9 and 10, which are, by the way, the exact same distance as here. And the edge 2 is 4 and 4. All right. Any questions about that process? Yeah. When do things get taken out? So what will happen next in the algorithm is we'll take 5 out. So you basically do this. Take something out of the fringe, process all of its edges, then take something out of the fringe, and then take something out, right? Yeah. No, we're actually finding the shortest path. The question was, are we trying to find the shortest path to some vertex? No. We're just trying to find the shortest path from 0 to everything. So is it different than if you're trying to find the shortest path to a certain vertex? A little bit, and we'll talk about how, but it just means you can quit early. So suppose we were trying to find the shortest path to 4, we would be done now already. Yeah, the shortest path's from 0 to everything. Yeah. So if you, say again, once... Yeah, so if you don't have any more edges for a certain vertex, will these ever change again? No. And actually what's really cool is that it's actually impossible that 2 could have changed. So it's not some... I'll mention it as kind of... I'll give an inductive pseudo-proof in a bit. But it turns out that any white vertex, once it's white, the edge to and distance to it they can never change again. So you didn't actually even need to look at the numbers. You could have just said, this vertex is white, so I know these values won't change. But that's something I haven't proven. Other questions? Yeah. How do we know that this gets us a connection to everything? It'll only work for all vertices that are reachable. So it doesn't necessarily. Yeah. If something's not reachable, it won't find something. But if there is a path, it'll definitely find it. Other thoughts? Yeah. If we have negative edges, this algorithm breaks. Then you have to use a different algorithm. Yeah. So the point of the priority queue is to not think about long paths. In a way, it's a way to cache or just to keep around information about who's close. You could recompute it every time, but it just makes things faster. It's redundant with this distance to array, but it's faster to access. Because if you wanted to find the vertex that's closest, you could actually just use the distance to array along with a marking value, but then you'd have to do time n or time v every time. And actually, Dijkstra's original algorithm does that. If you look at Dijkstra's original paper, he just looks in this array to find the next move. But the fringe speeds things up by it's a log factor. Yeah. So in real life, like in math and stuff, there would be like two-way roads. Yeah, in real life, there'd be two-way roads, and then you would just have, for every edge, an opposite edge with possibly the same weight, but not necessarily. Any other questions? All right, that's Dijkstra's algorithm. You know how it works now. All right, so then continuing on, just so that the completion happens, next vertex to come out is 5. So we consider vertex 5. It has no outgoing edges. Nothing happens. Next comes 6. 6 has one outgoing edge, and we do actually get an improvement. Next comes 3. 3 only has one outgoing edge, and it's impossible that it actually does anything because this vertex is already white, but hey. All right, so you can step through all this example again and see those extra steps I just blasted through at the last 5 seconds. But I don't think they're any more informative. Okay. So Dijkstra's algorithm is as follows. You visit your vertices not in depth first order or breadth first order, but in best first order. And that's actually the first week or two of CS 188 if you take it. So all these other best first searches. And then as you do it, when you visit a vertex, the action you take is relaxation. Okay, and what does relaxation mean? It means consider all of the edges and relax those. What does relaxing an edge mean? It means add it to the tree if it's better. Okay? And that means you have to track in some way a global list of the distances, and that's actually just an array of distances. So why does Dijkstra's algorithm work? Okay. Well, you have not necessarily taken CS70, so I'm not assuming that you're really fluid with inductive proof, so I'm only going to give you a proof sketch. If you take CS70, you will then take possibly CS170, and in that class, that's when you'll do the real heavy-duty proof. So for those of you who are like, oh, why is this hand-wavy? It's just because there's already so much in 61B, and 170 is going to go through it in more detail. But the basic idea is that Dijkstra's algorithm has the following property. When you take a vertex out of the priority queue, when you take X out, once it's been dequeued, you know that the path to X is optimal. And why does it work? Well, it's an inductive proof. So the source, you know that you have the best path, which is do nothing. And then for every vertex you take out, okay, so let's say we've just dequeued a vertex V. After we relax all of V's vertices, say it's the source, or say it's some later vertex, doesn't matter, then the path to the vertex at the top of that priority queue is also going to be optimal, okay? So that's the inductive proof, as you show that that's true, which I'm not doing right here, but that's the sketch of the inductive proof, okay? So basically, for every vertex you take out of the priority queue, you're adding one to the I am done with correctness club, and then you repeat that over and over until everybody's part of the closest club and you're done, okay? But you're not responsible for the proof, okay? What would this actually look like as an implementation? Something like this, okay? This is a little boring, but I think it's worth mentioning at least briefly. The code's not so crazy. This is pseudocode because it's like a little annoying to do inexact code in a slide, but basically you set up a distance to array, which is a bunch of doubles. Then you set them all to infinity. Those are all the distances, and that's everything but S. You then set up a bunch of edge to objects, and each edge is going to be some directed edge object. I mean, you could also give this as a vertex number, but I did directed edge to be consistent with the optional textbook. You create a priority queue, which has a special feature that it can have its priorities changed once an object's already in, and that was in one of the lab right before spring break, which was very sparsely attended, by the way. The lab before spring break. It was after the midterm and whenever everybody was gone, but hey. And then after you've created that fringe, you put all the vertices in it. As long as there's something left, you get the closest thing, and then you relax all of its edges. And then what does relax mean? Well, you just say, what vertex did you come from? What vertex did you go to? If that distance is better, so if the edge is better, then you add it to the shortest paths tree, which means changing those two values in the row. Okay? So again, don't look at all the little symbols here. This is just conceptual. The distance to something was equal to the distance to the old vertex plus the weight. The edge gets set. And then if the priority queue contains something, if it's still there in the fringe, you update its priority. And that's that. Okay, I'm not going to take questions on that because I think it's something to think about offline. What's the runtime of this algorithm? Turns out the analysis is actually pretty quick. The idea is if you think about what happens, you insert, so my cost model is operations on the priority queue. So insertion, we're going to put V things in the priority queue, and they're each going to take no more than log V time. Yeah, the first ones will be, constant time because there aren't that many. There's nothing in there yet, but we can bound above by log V. We're going to delete each item exactly one time, and that's going to be log V time. And then this decreased priority operation, in the worst case, we're going to do this big O of E times, and each one of those is going to cost log V in the worst case. And so the overall runtime, we're basically just counting insertions, deletions, and decreased priorities. So it's V, V, and E operations, and the cost for each is log V. So the sum total is going to be just adding all these up. So the total runtime is E plus V log V, and if E is bigger than V, it's just E log V. So that's the runtime. Now, if you don't have a priority queue, then it's E times V, and that's the old Dijkstra version, but you speed it up a little with a priority queue. All right, any questions about this? Something maybe to digest more later. Okay, so that's Dijkstra's algorithm. Now, here's another question for you. Dijkstra's algorithm, it will give you the right answer, but is it a good algorithm? Does it feel right? If you wanted to actually build this into Google Maps, do you think that if we're trying to find directions from, say, Denver to New York, do you think this will be correct? And do you think it will be efficient compared to some other hypothetical way of doing things? What do you think? Do you think it'll be correct? So it turns out Dijkstra's will definitely be correct so long as the graph is good and there's no negative edges. And there's no way that you go back in time driving, as far as I know. And will it be efficient? What seems inefficient about the way it might work? Yeah. Yeah, you'll be thinking about Denver to Phoenix on your way to New York because the way the tree grows is outwards, so we want to do a little better. So Dijkstra's will explore every place within about 2,000 miles of Denver, 1,778, modulo the fact that some roads have different driving time or speeds, and it'll take a long time to get to New York. Yes? Well, you can't avoid it just by marked nodes. You're still going to look in this direction. We don't have any way to take into account where we're going. We only think about source. Because Dijkstra's is travel outwards from the source, and so it'll just spread out like a spider web from Denver. So what we'll do as an alternative approach, what you've actually done in homework 4 already, if you've done it, and what you'll do again in project 3, is A star. So this is a preview of 188, and this is going to be even a little more hand-wavy than Dijkstra's, because I'm not going to prove this one at all. But with the approach here is, if we only have a single target in mind, back to your question over there, I don't remember where you were, was if we only have one target in mind, what can we do that's better, right? What's something that we could do just at a very hand-wavy approach? Like, what do you think we could do that's somehow better? Yeah. Yeah, we look at nodes that are like that are eastwards first, the ones that are going towards New York. Now, we can't only go east, because maybe it turns out that there's like a giant wall of fire that you can't drive across here, so maybe you have to drive around. But there still seems like there should be some way to take into account which way you're going. And so A star, it's a pretty simple change, but the proofs for why it work are a little tricky, and there's a lot of little subtle details here. But what we're going to do is, instead of visiting vertices and their distance away from Denver, we're going to go in order of their distance from away from Denver plus my estimate of the distance from that place to the source, or to the target, rather. Okay, so let me give you an example. There's, from Denver, 4 places we might go from this spot. Broomfield, Henderson, Aurora, Inglewood. Okay. So we could go to Inglewood, which is pretty close to Denver, but Henderson seems somehow a little better because it's in the right direction. So we might pick Henderson instead, and the way that we're looking at that is that we're going to sum the distance of Denver to Inglewood and the distance from Inglewood to New York, and we're going to compare that to the distance from Denver to Henderson plus the distance estimate from Henderson to New York, and that's going to tell us that Henderson seems somehow a little better, because that other term is going to be smaller if we go northeast. Okay, so basically, we'll look at some location if we already know the fastest way to get there, and we suspect that that place is better. That's the very high-level picture. Okay. So let me give you a little example of how this might work with A star. Same deal as before, but now we're going to be taking into account this heuristic. Now, I made this morning. I'm pretty sure it's not broken, but I apologize in advance if I never had a demo for this, but I think it'll help elucidate. So in this case, my heuristic, or this H value, my estimate, is I'm just going to say, these are just arbitrary, and it happens to be the minimum weight out of a particular vertex. So for example, 4, its biggest vertex coming out, biggest weight coming out is 5, and I just made that number up. It turns out that this H isn't really all that important. It just needs to have a certain property I'll describe soon. Okay. So we won't go through this whole example, but we'll just get the flavor of it, okay? So the source is closest, and in the fringe, everything has infinite distance. Now, what's different now from what we did before is that when we consider these 2 edges, just as before we said the distance is to 2 and 1, but now in the fringe, the only difference, literally between this and Dijkstra's algorithm, is that the fringe priority is not going to be the distance, but it's going to be the distance plus h. So 1, you'll notice, has the priority 2 plus 3, and 2 has the priority 1 plus 15. Okay? So what do we notice about this compared to how Dijkstra's ran? What would Dijkstra's algorithm go to next? 1 or 2? 2. However, what will A star go to instead first? 1. And the reason is it's saying, well, I think 1 is somehow better. I'm taking into account that this edge is only 3, this one's 15. Okay? Now that's not an answer, right? It's not obvious. Maybe this isn't a good way to go, but it turns out to work well in this case. Okay, so if I keep going in this case, we do the exact same thing, where all of these distances are computed in the exact same way. But again, the only difference between A star and Dijkstra's is the fringe priorities. So instead of 3 having priority 13, it has priority 15 because we add this heuristic. Now this number, again, it was just arbitrary. Any questions about this? Okay, so if you understood Dijkstra's, the only difference is that this value is summed with some arbitrary h. Okay, so why is this good? How could this possibly be helpful? How could this possibly work? Okay, I'm going to skip that slide for now. All right. Well, first let's talk about the heuristic. So how do we get our estimate? Where does this magical h come from? Like in the other example, it was like, okay, Josh, you made up some h that just magically made things work better. Well, it turns out that heuristic, I mean, it's just a word in English, like at once, like a thing we all know. All right, anyway. Heuristic, it's using experience to learn and improve. So we're just going to use our knowledge about how the world works, and I'm going to say, okay, for this map to the right, what do you think we could use for the heuristic? Straight line distance. So I could say, I'm just going to imagine that I take or the crow flies distance, where I say, if a bird were to take off from Henderson and fly to New York, what's the distance going to be? And that's not the right distance, because the real distance involves roads, and there may be mountains in the way, and lakes and everything, but it's a rough estimate to say, well, just imagine you're a bird, okay? And so in this case, the method that computes the heuristic just calls some helper function that computes the line distance between the vertex that we're considering and our goal, in this case, New York City. Okay? Yeah. Yeah, so for A star to work, you have to have an end point. Otherwise, it doesn't work. Mm-hmm. So in my haste because I was running a little low on time, I did not mention that we had a specific target, which was up here. Goal is 6. Okay, good point. Yeah. Yeah, so if you have a bad estimate, things can go wrong. So let's talk about bad estimates first. Let's suppose we make the estimate that everything is 0 away and everything is, say, 10,000 away. What will happen? I'll only give you 25 seconds on that one. Do you get the right answer, I guess, my first question? Okay, so if you say h is 0, what happens? You get Dijkstra's. What about if h is 10,000? You just get Dijkstra's. So it turns out that both of those bad estimates just give you Dijkstra's. So it seems like the heuristic might not matter, but here's an example that's a little spookier. Okay, let's suppose that you're just a chauvinist about the Midwest, and you're like, nobody should live out here. They say the word pop, it's weird. So what we're going to do is we're going to say any city here is going to have a heuristic value of 1 million. So in that case, the search, you get here and it's like, it's not so good. So you go around. Okay. So in this case, is their algorithm going to be correct or does it just run slower in terms of finding best driving directions? Well, it's slower for sure. Is it still correct? 100,000 miles. It will quit as soon as we get to New York, yeah. Yeah, it would not be correct, because the distance from Denver to New York is less than 100,000 miles, and the best route does actually go through somewhere near Chicago, okay? So our middle of nowhere estimate, where we said the Midwest sucks, right? In that approach, it doesn't work, and it makes A star break, okay? So there's some little terminology for you. A heuristic that overestimates is called inadmissible. That's pretty bad, right? You don't want to be inadmissible. So what I'll tell you is that A star works so long as the heuristic is admissible, and that just means it never overestimates. So in other words, for every single point in the entire universe, it never overestimates the distance to New York, it'll always work. And so if we look at this little example I had here, where I said that the heuristic is just the smallest edge coming out of the vertex, that is an admissible heuristic because there's no way you're going to have anything faster from you to the target that doesn't involve using your smallest out edge. Yeah, that's kind of the idea. All right, any questions about that? No. So there's a really cute, if you guys want to explore a little, I'm not going to do much with this, but I'm just going to mention that there is a nice visual demo where you have a source and a target, and you can run a bunch of different search algorithms, the ones we've discussed in class and others. So if I run Dijkstra's, for example, from source to target, that's the way it searches, right? It goes right into these mountains, and it searches in a slow way. Still finds the right answer, but it considers a lot of routes that weren't useful. It goes to the left, okay? Now, if we do A star instead, where we use a specific heuristic, it's much faster. It searches some stuff that seemed a little silly, and there's other approaches, okay? So that's just kind of a fun point. And if you think about what you did on homework 4, it was actually all of this. Okay. I won't say much about this summary slide because I actually kind of want to mention the homework 4 thing in our last 30 seconds, which is the slide I skipped earlier, which is you've actually done this. Okay. So in homework 4, you did A star, where the priority queue was nodes in order of moves so far and estimated distance. In this case, the graph was stored implicitly in neighbors, and then all distances were always 1, like the weights from edges were always 1. Okay? And so you can think about this as a different way of looking at A star. It's a really handy algorithm, and that's it for our shortest paths, and I will see you on Wednesday.